Welcome to WildFacts. So today, we're going to be doing a Matt Parker, or in other words, giving it a go. The specific problem we're going to be taking a crack at is the Collatz conjecture. I figure since most pop science channels have explained the Collatz conjecture to death, I'll do my video on my best attempt to solve the Collatz conjecture instead of just doing another explainer. Also, I'm curious as to what new things other people may have found, so be sure to comment. With nothing left but to get started, welcome to WildFacts. First thing I'm going to do is rule out unbounded infinite trees. And to do that, I'm going to contradict Terence Tao's result. In 2019, Terence Tao proved that as you approach infinity, the number of members that belong to the set of numbers that do reduce to 1 approaches a density that is asymptotic to 100%. We also have to note that the growth rate of the Collatz function is exponential. There's a lot of complex dynamics that goes into calculating this exponential growth rate, but since 1 in 6 numbers produces 2 parents while the others produce 1, that leaves at least a lower bound of exponential growth of 1 and 1/6. In order to find the growth rate of the Collatz function, you first have to find out how many integers have x stopping times. And as x approaches infinity, you take a ratio of x over x minus 1 for however many integers belong to each of those stopping times. This is conjectured to approach a closed form value of 3 plus the square root of 21, all divided by 6. The first 3 digits past the decimal point is 1.263. For my purposes, the precise value doesn't matter. All that matters is that the growth rate is exponential. This growth rate can be visualized by building the Collatz tree in reverse, starting from 1 and reversing the functions, and building all variations. Every layer upward is one more step to the stopping time. The reason for all this setup is if we are to assume an unbounded tree exists, since the growth rate is defined by the function itself, it would necessarily have its own exponential growth rate. And comparing two exponential growth rates by their ratio will necessarily produce a positive density for both numbers, even if the number is tiny. This contradicts Terence Tao's result, therefore ruling out all unbounded infinite trees. The last thing to do is ruling out non-trivial cycles. This is when I started looking at the symmetries of the function. This is so I could understand why the trivial cycle is there. The fact is, it's a continuously iterative function, meaning it must continue to produce solutions, so there are only 2 possibilities. Either it falls into an infinite regression of non-repeating solutions, or it falls into a cycle, either a cycle of 1, where x equals x, or a cycle of 2, or a cycle of 3, like the 4-2-1 cycle in the Collatz function. I realize that this is true. I should be able to reformat the Collatz function so that you only need 1 rule instead of the 2 rules for odd and even numbers. The point of doing this would be to show that the function can be reformatted so that the iteration process only causes the value to travel in one single direction, either increasing or decreasing. So that's what I did. This is the new function, 3x plus 2 to the n. Here, 2 to the power of n is the value of 2 in the prime factorization of the seed number. If the seed number is odd, then n equals 0. The halting criteria for this function is reaching a power of 2. And the halving steps are preserved within the exponent of the increasing power of 2. And the number of steps it takes you to get to that power of 2 will be the number of your tripling steps. When viewing the numbers by their prime factorization, the odd portion of the prime factorization evolves exactly as the original Collatz function. The only difference is the power of 2 is consistently increasing, preserving all the halving steps. This ensures that the Collatz function reformatted in this way always increases in value. Now, it's important to note how the non-trivial cycle manifests itself with this new one-rule format of the Collatz function. When this function halts at a power of 2, the cycle manifests itself as what would be an increase through powers of 2 by increments of 2, or equally by a power of 4. Then we must note that if we assume a non-trivial cycle exists, there cannot be a power of 2 in that non-trivial cycle, because that would necessarily cause an intersection with the trivial cycle. But since in the new format of the Collatz function with one rule, converging to a power of 2 is the equivalent of the original function reaching 1, which means if a non-trivial cycle exists, it must exist within an unbounded tree. And we already proved that unbounded trees can't exist because they would contradict Terence Tao's result.